Okay, please settle in. Okay, let's get started. Okay, we have a very exciting session. Okay, the first talk, I think yesterday Ian asked about AI. I think Alex is going to address that directly. So Alex will talk about novel approaches to cosmological constraints.
So good morning, everyone. First, I'd like to thank the organizers and, of course, Subir in particular for organizing this very exciting meeting. It's very nice to be back here after so many years and meet all the different people that it's very nice to meet from time to time and be back in India. So in the spirit of the meeting, I'm going to talk about rethinking how one can get cosmological constraints out of our experiments. And I'll do this in the context of both the current and the future cosmological surveys that we're analyzing now and that we are planning to analyze in the future or soon. And a lot of the work was done by PhD students and postdocs, whom you can find here at ETH. Some of them have moved on to faculty positions in different institutions. So our main goal is to try to not only constrain our cosmological model, but more importantly, challenge our cosmological model to try to see whether we can find new physics and perhaps change the foundation of our understanding of the universe. Now, in order to learn about the universe, what we do observationally is we combine different cosmological probes. So here I've organized them in sort of 4 categories. So first, there's the cosmic microwave background that gives us a picture of the universe at recombination, and in particular of the fluctuations at that time. Then there's a class of probes, which we can call geometrical probe, that probe the background. Example of this being supernovae, now gravitational waves, for example, standard sirens, that give us information about the expansion of the universe as a function of time. Then there's a set of probes which are based on visible tracers, and for which we can measure the clustering of matter, assuming a relation between the underlying density field and the tracer. This can measure the density field, also the velocity fields, as we've heard yesterday. And then there's also gravitational lensing, which uses the perturbation in the propagation of photons along their trajectory in an inhomogeneous universe, and that can give us information about the mass distribution in the universe. And it's by combining these different probes that we have built the standard model and how we can challenge it. And it's important to combine them not only to improve our uncertainties, our statistical uncertainties, but also to check the systematics, and also, as I will show later, to test the physics, the fundamental physics of our model more thoroughly. Now this is, of course, under immense progress in the last decades, and it will continue in the next decade. We've heard this yesterday about the amazing measurement from the cosmic microwave background and isotropies and the various experiments that are being planned. In the visible and near-infrared, we have galaxy surveys, which are either imaging or spectroscopy or a combination of the two, which we're analyzing now. We've heard about DESI, for example. We'll talk about DES. And there's a future LSST, Euclid, Raman, Subaru, which Subaru is actually present, experiment, that will improve not only the redshift reach of the galaxies that we can use for large-scale structure, but also the number of galaxies available and therefore the Poisson noise. And there's a synergy between both imaging and spectroscopy that give us complementary information. And there's very exciting prospects for the radio. It was briefly discussed yesterday, and there will be talk today about this. The radio can be used to bridge the gap between the CMB and the visible near-infrared galaxy surveys, and give us information about the formation of structures at intermediate redshifts through, in particular, 21 centimeter intensity mapping. I'll be focusing primarily on this galaxy surveys and this cosmic microwave background, but if you're interested, I can also discuss this as well. Now let's start with gravitational lensing, and then I'll build it up from there. And I'm going to show you how one can both extract more information from existing probes and also combine them in a much more integrated way to get further test of our model. So let's start with gravitational lensing. So gravitational lensing can be measured by measuring the shape of distant galaxies. And we can the observed shape of galaxies are affected by the structures along the line of sight, in particular by mass inhomogeneities. And what we can do by measuring the shape of a very large number of galaxies, we can make map of the projected matter density on the sky. What you see here is one of the largest such map that has been done with the Dark Energy Survey. This is from the year 3 data release. This covers about 4,000 square degrees. You see the footprint of the Dark Energy surveys, and you see in sort of yellow color the overdensities, the projected overdensities, and in darker color the projected underdensities. Okay? So what we can do is we can take this map, analyze the statistics of this map, compare that to prediction from theoretical models, and obtain a constraint on our cosmological model. Now we can do more than just analyzing this map, because what we can do is we can do what is called tomography. So what we can do is we can take our galaxy sample, use multiband imaging to obtain photometric redshift, and then bin the different galaxies into different redshift bins. You can see here it was divided into 4 bins at different redshifts. And then we can analyze the map for each of these galaxy subsamples that give us, in this case, 4 maps. And we can also look at the cross-correlation between the map that give us further tomographic information. And what you see here is a measurement of, in this case, the 2-point function. This is a correlation function in real space of this distortion, which is called the shear. The shear is a spinless, is a spin-2 massless vector. So there's actually 2 quantities, so we can make several, we can build several correlation functions. 2 are relevant, and then what you see here on the diagonal here is the measurement of the autocorrelation of the shear, of one of the correlation functions for the shear in each of the bins, so 1, 2, 3, and 4. And then you see the autocorrelation for another correlation function here. Again, autocorrelation for each bin 1 by 1. And then the off-diagonal plots corresponds to the cross-correlation between different bins. So you see we can measure quite a lot of correlation functions, and then we can compare that to theoretical prediction that you see in green. This is, in this case, it's for the lambda CDM model, and constrain our model. This is a classical, what I would call a classical analysis, and this has been very successful. There's been now various surveys that have successfully detected a signal with very high signal to noise, and we can now get strong constraints on our cosmological parameter. The parameter we are most sensitive with is the amplitude of the matter perturbation, which makes sense because this is what's generating the lensing. It's usually characterized by the sigma 8, which is the RMS fluctuations of the density on 8 megaparsec scale. It turns out that the constraint on sigma is also degenerate with omega m. So what we get is degenerate constraint between sigma 8 and omega m if we use only a 2-point function. So what you see in green here is a constraint from the Dark Energy Survey. You also see in red and in blue the constraint from other surveys, point in particular to the KIT survey, which tends to be a bit lower on this plot. And then this can be compared with the constraint from the Planck CMB measurements, which are give us an amplitude of the fluctuation at redshift 1100, but that can be propagated forward in a model-dependent way, and we can compare it with the measurement for lensing. And you see that the small difference, it's not very significant. This is what is usually referred to as a sigma 8 tension. What you see here is the same information displayed in a different way. So we can define this S8 parameter, which is sigma 8 times omega to some power about 0.5 or so. It's just a way of flattening the plot on the left, and sometimes more convenient to consider S8 as opposed to sigma 8 because it gives us more the amplitude of the lensing signal. And you see also Planck and DES, and again, kids here in blue. Okay. Now what we can do is we can add further information from a galaxy survey. So not only can we measure the shape of galaxies, but we can also measure their positions, at least in 2 dimensions, in different bins. So we can get a tomographic measurement of the clustering of galaxies, and we can add this to the weak lensing signal. This is all, by the way, from the year 3 data release from the collaboration. So what you see in blue, again, in this sigma 8 omega m, or if you prefer S8 and omega m, in blue you see the constraint on omega m and sigma 8 from weak lensing alone. In red, you see what happens if you consider the clustering of galaxies and the cross-correlation between clustering and weak lensing. And then if you combine all the information together, clustering and weak lensing and the cross-correlation, then we get the gray contours, which are an improvement over the weak lensing only. Of course, there's also a large amount of analysis to control systematic error in both the weak lensing and the clustering, and this is marginalized over nuisance parameters that control the systematics. Yeah.
Does the bias of the lens sample play a role?
Yes, so the bias is one of the parameters that we marginalize over. Exactly, yep, absolutely, yep. Now, if you go back to, let's say, the S8 omega m plane here, we can again compare with Planck. You see Planck in green, and the DESI joint analysis weak lensing plus clustering in gray, and you see there's again a small tension, not very significant, and you can, if you combine them together, you get the orange contour. Now, when this came out, this was quite exciting because you see, at least for on this parameter plane, so green is DES only, right? Clustering per weak lensing. There's only galaxy survey information. Sorry, in green is the CMB, and in gray, I mean, is the DES only. Green is the CMB. And you see that the contours start to be of comparable sizes. So these galaxy surveys are starting to reach the point where the information content starts to be comparable with the CMB. Of course, we're not exactly considering the same parameters and so on, but we're getting into the regime where we can get complementary information at high redshift and at low redshift. This analysis is called 3x2 because there are 3 correlation functions. One for the lensing, galaxy-galaxy, and galaxy lensing. In reality, there's much more than that, right? Because you have several correlation functions for the lensing, or several shear components, and you have the tomography, so you have actually many correlation functions. But we call that collectively 3x2 when we denote the 2-point analysis of 2 probes, including the cross correlations.
The intrinsic shapes are randomly oriented, assumed to be.
So the intrinsic shapes are not assumed to be randomly oriented. We take into account what is called intrinsic alignment. There could be a physical correlation in the shape of galaxies, right? In fact, there are. It's been well measured now. But we separate that from the weak lensing signal because it has a very different redshift signature. At least one component of this intrinsic alignment signal is important when the galaxies are close together. However, the lensing signal is coherent over very large redshift because the light goes through the same structures. So by using this tomographic information, we can disentangle the intrinsic alignment from the lensing signal, but this is a major source of systematic uncertainty.
And that we marginalize over?
Marginalize over, sorry, yeah. And that we look at different models, different level of complexity to see whether our results are robust to changes in the modeling of the intrinsic alignment. That's a very important part of the analysis. Yeah. Okay. All right. Now, a very recent result from the KIDS collaboration is shown here. So the KIDS collaboration has reanalyzed its weak lensing signal in a survey which is 1,300 square degrees. They call it KIDS Legacy. This is their last analysis. They're not taking any data anymore. And you see an update on their constraint. This is, again, S8 versus omega m. In green, you see KIDS. In the small contours in orange is the Planck legacy, the latest analysis, PR4 analysis of Planck. And you see that their weak lensing constraint have gone up. And now there's even less, basically no tension between KIDS and Planck. KIDS was the one in the, which...
Can you sketch where they were before they reanalyzed?
So unfortunately, they didn't overplot it, but maybe we can compare.
They probably were embarrassed to overplot
A little bit, yeah. So this is the old one, and now they're more compatible with this. Okay, and this is coming.
What did they find that was the?
It's
I shouldn't
it.
be interrupting, but what
No,
did
no,
they
that's
find
fine.
that was the problem?
Yeah. So there are several effects, but the primary effect is a recalibration of the photometric redshifts. Okay, the photometric redshift has to be so these distributions have to be calibrated very carefully because the lensing signal depends on this. The higher the redshift, the stronger the lensing signal. And that's another very intense effort for systematics control, which is the calibration of the photometric redshift. They've improved it, and they find this change, which is quite a change. For those of you who followed for a long time, the so-called sigma 8 tension was driven by a tension between Kidd and Planck, basically between the blue contours and the orange contour. And at the end, this has gone away. So I would say the sigma, and you see DESI is a little bit lower, but not significant either. There's also another measurement by Subaru, also quite compatible. So I would say the sigma 8 tension has mostly gone away, basically. Okay? Which is good for lambda CDM, but not for challenging it, but I'll come to that. Okay, so now this is using the 2-point function, right, which captures some information on these maps. But there's more information in the maps than just captured by the 2-point correlation function or power spectrum, if you prefer. And this is coming. This is because of nonlinear structure formation. So here you see a simulation of structure formations starting from small Gaussian initial condition until late time, and you see this cosmic web that Dick has described yesterday with this filamentary structure, which is a signature of gravitational instability in an expanding universe. And this is a very non-Gaussian field. The field is very non-Gaussian. And in fact, what we can do here is we can take a slice in this simulation and we can compare the distribution, also at least the statistical properties or the texture visible by eye of this n-body simulation compared to a Gaussian random field that has exactly the same 2-point function. Okay, so these two have the same 2-point function. And you see that the texture is quite different. If you measure 2-point function, it will be the same. But you see that the fully nonlinear evolved field has a lot more texture. In fact, it has peaks and filaments, which are reminiscent of the cosmic web, which are basically, these are basically halos and filaments, basically, which are projected. In this case, it's a slice. But and so one of the questions is how can we take that into account and extract more information from our from the maps that we have, so that we can improve upon the constraint that we get from the 2-point function only. Yeah.
So was this non-Gaussian n-body simulation just to prove a statistical point, or did you?
It's a.
Was this just an exercise to prove a statistical point?
It's just visual.
Okay.
This is just visual. Yeah, this is just to show the difference. Yeah, of course. Yeah, yeah.
Interrupted. So you do this, as you must have done by phase scrambling to get the Gaussian random.
I think this we just realized we took the power spectrum and did a Gaussian realization. It's not even the same
Well, that
phases.
is in effect what it
Yeah,
is.
yeah, effectively, yeah.
The interesting question is, I think that the texture will always look the same if you did a different realization. That is to say, but that could be wrong. I mean, you can see a visual correlation between ups and downs, and yet the phases have been scrambled. And so the issue is whether the different Gaussian random simulations with the same power spectrum would in effect look almost the same.
The same as this one, you mean?
Yeah.
Yeah, so it would look, the texture would look very similar. Of course, the phases were different.
Well,
Yeah.
for example, there are little holes in the n-body simulation.
Right.
And they're sustained, although much fuzzier, in the Gaussian random field one.
You mean
I'm looking over in
the same
corner.
location, you mean?
Yeah.
So no, that's fortuitous because we have completely different random seeds here. The phases are not, the amplitude of the modes are not kept. So this is a completely different realization. So this is completely, it's just yeah. This is your there's no correlation. These two maps have no correlations. Yeah, again, it's just for visual impression. Okay, so how can we capture this non-Gaussian information? Well, one can use various statistical measures that can capture this information. It turns out there are many. We can go to high-order correlation function. We can do Minkowski function. There's a whole a series of various statistics we can use. It turns out that there's a very simple one which is very powerful and captures a lot of the non-Gaussianity, and it's peak statistics. So the idea is to take a map like this. So this is a DS observed map. And then what we can do is we can identify the peaks in this map, and we can count the peaks as a function of their amplitude. Okay, very simple. So we should do a peak detection algorithm, measure the amplitude. And then in each of these, and remember we have 4 maps because we have 4 different redshift bins. We can measure, this is a renormalized version of the number of peaks as a function of the amplitude of the peaks. And then we can do it for each map. We can also look across map. We can take the product of 2 maps and look at the peaks in the product of 2 maps to give us what's so-called cross peaks. And then we can compare that to some predictions and then obtain constraints on parameters. What you see, for example, this is a measurement. This is from one of our students, Dominic Zerker, who did this analysis within the DESI collaboration. You see the measurements, and you see also the different predictions which have different values of this S8 parameter. And you see that the amplitude of the peak statistics depend on the S8 parameter and many other parameters as well, of course. Now sorry?
Did you smooth the field?
Yes, so you smooth it.
So what is the scale?
This is a couple of arc minutes, I think, 3 or 4 arc minutes. That's because we want to be independent. We want not to be sensitive on baryonic physics. So we smooth quite conservatively to avoid having to marginalize over baryon.
What field?
I think here he used the Gaussian filter. Yeah, I think so. So we control the scale that we use by smoothing. Basically, we don't want to include the small scales. First of all, they're very noisy, but also they're more as we go to small scales, there's more and more systematic, including astrophysical systematics. So we do a robustness analysis to test whether we're. And of course, exactly. So if you have to smooth all the way to very large scales, then you lose the non-Gaussian signal and you haven't learned anything. But thankfully, we have a range of scales where we can do the analysis and gain, as I'll show you in a minute. Now, the issue with this is that we can no longer make a theoretical prediction of the peak statistics. It's a map-level statistic. It depends too much on the detail of the analysis, the way we implement the peak finder, the different survey mask, and so on. And therefore, one needs to rely on simulations in order to make the prediction about the signal that we expect for a given cosmological model. So what we do...
So what field is it?
Sorry?
You said E.
Kappa. So kappa is the convergence field.
The E, what does that signify?
Peaks
E.
E.
E is the E mode. So it turns out that the shear field can be turned into E and B mode, just like the polarization, and we keep the E mode, which is, I know the way we check for systematics, because in weak lensing, the weak lensing only generates E modes, no B modes. Yep.
Did you try to expand the neutrino?
For the distribution of the...
The number of peaks as a function of height.
So there's a lot of work with the probability distribution function using Hermite polynomial. That's another approach, not in here, but there's another way of characterizing the non-Gaussian information.
Gaussian correction is not very large.
Yeah. So there's also a work in the DESI that does this. Yep.
Last question, is
Yeah.
the B mode consistent with 0?
Yes.
That is checked.
Oh yeah, that is checked. That's one of the major systematic check. There's also check on various cross correlation with the PSF, with all sorts of things. Yeah. So this is a 40-page analysis, many years. Here we're looking only at the maxima, but one can also apply this to minima as well. Some people do so-called voice statistics in this way. Yeah. Okay, now as I said, in order to compare that to a prediction, one needs to make simulations. So what we do is we make a simulation of the DESI survey using n-body simulation. We project onto weak lensing maps. Then we add all the relevant systematic effects like the noise, the PSF effect, the sensitivity, and so on. And then we can generate simulated surveys. This is an example of one of these surveys, and you see we use the same mask and the same noise statistics and so on. So we model all this, and then we can measure the peak statistics for the simulation. We can vary the cosmological parameters, and then we can get constraints on the cosmological parameters. Okay, this is called simulation-based inference. This is a regime where we can no longer make predictions for the statistic we're measuring analytically, and we do it via simulations. Yeah.
So when you use an n-body simulation, does this n-body simulation contain any baryonic?
So the n-body simulation does not, but we have a prescription for adding the effect of the baryons onto the density field of the n-body simulation. The reason we do this is because putting the baryons is very expensive. The hydro simulations are very expensive, and we need many, many, many simulations. So we have a prescription to do it very fast, basically. And we marginalize over the parameters that control the baryonic physics. Now here what we do is we use it only for testing. So we turn on and off the baryonic physics for different values, and then we choose a smoothing scale so that we're not sensitive to the baryonic corrections in this particular case.
But how do you know some of your non-Gaussianity is not an artifact of that?
Of the baryons.
The prescription for putting in baryons.
Of course. So you have to use, of course, yeah. So you have to use some knowledge of the baryons. Thankfully, we have quite a lot of knowledge on baryons. I mean, we know where the baryons are in observations. They is either hot gas that we can probe with the Sunyaev-Zeldovich effect or the X-ray emission, and there's also the galaxies. So we use priors from of our knowledge on clusters, groups of galaxies and clusters to inform the baryon model that we use, and then we marginalize over the parameters that are left uncertain from our knowledge. So it's a phenomenological, semi-phenomenological model for the baryon that we use. But we're very conservative, as I said. We turn on the baryons, we change the parameters, and then we choose the scale, because the baryons are only important on small scales. They follow the baryons, the dark matter on large scale, but not on small scales. So we tune the smoothing scale to get rid of scales that are sensitive to baryons, basically. Okay? But that's and that's true for the two-point function as well, by the way, same thing. Okay, baryonic corrections is yet another systematic that we take care of. Okay, I have to move. So this is the result. So what you see again in the sigma 8 omega m plane here, you see the peaks statistic in orange, and you see that the two-point function in blue has much larger contours. This is a comparison between the two-point function on measured with exactly the same scale cuts. And you see that the peaks can improve on the two-point function, and then if we combine the two-point function and the peaks, we get the green contours, which are even more constrained. And in this case, we found also a value of sigma a little bit higher that even reduces the tension with a Planck, as you can see here, even more. Now, can we go a step further? Now, until now, what I've showed you is that we take a weak lensing observed map. We measure a summary statistic, the two-point function, or the peak statistics, for example. Then we make a theoretical prediction. For the two-point function, we can make an analytic prediction. For the peaks, we do it through simulations. And then we derive a likelihood, and then we get cosmological constraint for a given model. So the idea is to see whether we can improve upon this and to see whether we can capture even more non-Gaussian information in the maps. And this is what we've done using machine learning. So the idea is to replace what we call human-made statistics. So these are some humans that have defined some statistics that are two-point function, peaks, various other. So here we're going to do learned statistics. Okay, learned statistics. So the idea is that we generate a very large number of simulations that have all the physical effects, and then we tell the convolutional neural network that this simulation looks like this, and these are the values of the parameters. This simulation looks like this. These are the values of the cosmological parameters. We train the network, and then we give it the real image, and we ask it what are the values of the parameters, and it derives constraints. Okay. So in this case, we completely replace the human-made statistics with machine learning learned statistics. Okay, so does it work? The answer is yes. This is the work of another student, Yanis Fleury, who did the first analysis on real data using machine learning. This is on the kids 450, an earlier version of the kids survey. And you can see that the constraint again on sigma 8 omega m. And you can see the constraint from the 2-point function. Only this is for rather simplified treatment of systematic, so it doesn't have all the systematic treatment that we have before. But at least we could see that the blue contours, which is the machine learning constraints that can potentially capture non-Gaussian information, improved above the green contours, which is the ones coming from the 2-point function only with the same scale cut. So we see that the fact that it has improved, it means that the machine learning algorithm has captured non-Gaussian information, and therefore it can go beyond the 2-point function information. Yeah.
Can you just unpack that a little bit? So did you train the neural networks on simulated data with different parameters?
Yes. So thousands and thousands of simulations like this. But for the simulation, we know the value of the cosmological parameters. We know the value of the systematic parameters. And we train the network to be able to go from the map, directly from the map, to the parameters.
So it's supervised learning, but without going through the spectrum.
Supervised learning without going through anything. That's right. It's a pure convolutional neural network. How do we get the? Yeah, very good. So we have different ways of doing it. In this case, we're using an approximation to likelihood. Now we're using simulation-based inference with normalizing flows to model the likelihood. So we do a simulation-based inference. I'll be talking a bit more if I have a minute. Yeah.
So just request to let me finish. And
Yeah.
we can have more questions.
Okay. So then this was relatively idealized conditions. We only had 2 parameters, sigma 8 omega m. So what Yanis did after this is to do a full analysis with the same condition, the same systematics, the same number of parameters as was done for the kids 1000 survey. In this case, analyze a WCDM model. And what you can see is that you can see his constraint in blue compared to the power spectrum in black. This was a blinded analysis, so he didn't look at the result before. He didn't look at this result before unblinding. And you see that there's a very good agreement between the neural network and the 2-point function. The controls from the neural network are a little bit smaller, but not very much, because we had to be very conservative in the scale cuts, and therefore we didn't have that much non-Gaussian information. In green is the official kids 1000 collaboration constraints, contours using the 2-point function, but with more aggressive scale cuts because they could model it more carefully. And in this case, it was a WCDM analysis, so we even had the W model here. So what we're in the process of doing is applying this to DS year 3, which is, remember, more than 4,000 square degrees. And this time we're going weak lensing and clustering together. So it's another student, Arne Thompson, who has done a extensive now simulation on simulation validation of his technique. And this combines weak lensing, clustering, the full forward model, all of these both techniques, of these both maps. And then we use machine learning inference. And you can see the result of his simulation validation here. So what you see is the parameters some of the parameters that is constraining. Again, you can look at S8 omega m, for example. In black is what we get from the 2-point function with exactly the same cuts. And in green is what we get with his machine learning learned statistic framework. And the truth here is the parameters from an external simulation called the Burzer simulation, which is a mock simulation which is used by the collaboration. It has nothing to do with our simulations. And we use it to validate the method. How much time do I have?
Well, technically 1 minute, but since
Take
there are
1 minute.
questions, maybe 2 more minutes.
Okay. So in order to do this, we have to, the price we pay for getting more information is to we need a very large number of simulations. So what we've done is we've built this CosmoGrid suite of simulation, which has 2,500 cosmologies from which we can generate various initial conditions. And then you can see various simulations here, and this is what spanning a parameter space, in this case JWST, and then we can use it to train our machine learning or do peak statistics. And then from the light cone of this simulation, we can generate maps of the different probes. So we can generate maps for the weak lensing, we can generate maps for the density field, and using a bias model, we can get the density field. We also generate maps for CMB lensing and also for ASW. And then in the future, we will integrate all these different probes together. I won't have time to show you analysis of two-point function using a multi-probe, but if you're interested during the break, I can show you a joint analysis between CMB, 5x2-point function, including CMB lensing, ISW, clustering, a tomographic analysis, and I can show you the constraint. Unfortunately, I won't. I'm running out of time. Thank you.
Questions? Well, maybe let me start with someone who's not asked. Yeah, Arman first.
Okay, thank you very much for the talk. I mean, all good about the machine learning and simulations, but all those simulations are also based on some underlying cosmology model.
That's right.
And when you compare it with the actual data, we don't know what is the underlying cosmology model.
That's right.
So how can you use those simulations based on some cosmology
very
for
good.
the data that we don't know?
Yeah, so if I had more time, I would talk more about this. So of course, this is simulation-based inference. So what we can do is we can test the model within we can test whether the data is compatible with a set of models, basically, right? So there are two ways to go about it. Either we look at extensions, right? So we can look at an extension and get the constraint for the extension, let's say dynamic or dark energy, for example. And then we can constrain that and see whether it's compatible with lambda CDM, for example. Or we can do something we're working on, we can do model testing or model rejection. We can say, is the data compatible with this set of simulation, which spans all the parameters within the prior of a model. And in machine learning, there's interesting techniques to do this, so we're working on this. For the moment, we're doing everything within models, but we're considering extensions. Yeah.
So for very selfish reasons, are the Cosmogrid simulations available, including the...
it's all public.
You know where I'm going with this. So.
Yeah, of course. Okay. We can discuss it, but this is all public, and the code also, this UFalcon to make the maps is also public. Okay, all of this,
thanks.
But we can discuss.
I'll talk to you.
Yeah.
Yeah, very quick, since we're short of time. This machine learned inference, the statistic that the neural network has learned, is it possible to then open that black box, learn what statistic, approximately even learn what statistics it has inferred, so that we can learn some statistics, not just the machine?
So not this one. This is called interpretable machine learning, where you want to get the machine learning to tell humans what it has learned. And there are techniques and even machine learning models that can do this. They're called interpretable machine learning. They give you the kernels. They give you a heat map of what they detected. So we looked at this, and when it's a bit hard to interpret. The problem also, if you impose this on the machine learning algorithm, they don't do as well, it turns out, because they're more constrained. So in this case, we didn't do this. What we did is a very interesting analysis where we took weak lensing data. This was simulation on simulation, and then we removed information from it. So for example, we scrambled the redshifts. We scrambled the pixels. We removed the phases, and we saw the result on the inference. So it's kind of a reverse engineering approach, and we could learn quite a lot about this. But that's the thing that's why I wanted to show the progression between the classical analysis, where we have a theoretical prediction, to the simulation-based inference, where we can only predict with simulation, and then the full machine learning, which is a black box. You can potentially learn more and more, but at the same time, your control on the prediction goes down. It doesn't mean there's no physics, so that all the physics goes more and more and more into the simulation. In fact, I would argue that you can put even more physics, because in the simulation, you can add very complex nonlinear effects, partially instrumental effects. And this is a new paradigm that we have to get used to, how far we're going to go in that direction. Of course, for the moment, we're going to do all of that, right? And eventually, we'll be able to in my view, get very strong tests of the standard model. and be able to discriminate the different models in this way, because we'll be able to capture also nonlinear dynamics.
Asim?
I have the same question.
Okay.
Yeah, Ian?
Yes, hi, thank you. Wonderful talk. I wanted to ask on the same line as Arman asked. So, given that your weak lensing maps are so big and and you could potentially do your SBI with millions of different data sets and cosmology, can you please comment about the overhead computational charge and how feasible physically that is?
Huge.
I think.
That's another price you pay. Not only you lose control on your predictions, but you have to get a very large computing resources in order to do this. In order to generate this cosmogrid, it was month and month of multi-GPU calculations on a supercomputer in Switzerland. So we're mostly limited by compute, actually, not by the algorithm.
Exactly. Is that like a physically feasible thing in the future?
I think it's feasible because we have now new generations of computers, in particularly GPU chips, as well as new accelerations of the code.
Yeah.
And
while he's setting up, you can take one or two very quick questions. Yeah.
And we can definitely go much further than this. Already with the new generation of computers, we can now consider a higher resolution, so we can go to small scales and span larger parameters. For the moment, we're not limited. Let's put it this way. Computing is the limit, but we can still push it much further than we have done now.
Okay, so short.
Prices for RAM, right?
It's getting expensive, but
Were you going to comment on this unexplained overall shear in the field?
So
which
that's
is not a B mode, but
yeah,
it's
exactly.
a E mode, I guess.
Exactly. So so that's an embarrassment.
Well, this is what you want to know about.
Yeah. So if you look at so what I showed you is a map made by looking at the shear, and what you can do is you can average the shear over the entire region. Now in lambda CDM homogeneous isotropic, this shear should be very, very small, because you average over such large volume. And in most weak lensing analysis, we get a significant mean shear, okay? And we kind of forget it, and we continue by looking at the two-point function, basically, not the mean. We subtract the mean. Now, where that comes from, it could come from physics, of course. It could also come from systematics. The fact we have so many galaxies, we average so many galaxies, that our error bars on the mean shear is extremely small. So it's much more stringent test than actually the test that we're doing on the two-point function. And there could easily be residual systematics on the PSF correction and many other effects at that level. But this is something that we find in most cases.
I saw it was about 5 or 6 times your estimate of the uncertainty, the systematic.
Yeah, so the mean shear is typically very significant.
Factor of 5 is rather large.
Yeah, it's very large and very significant.
So maybe we can discuss this already 2 minutes late. So and there are more questions also. So let's thank Alex again for a very nice talk.
So that's swept under the rug.
You have somebody working on that.
Yeah, so please start. So next talk is by Changbom Park on most probable behavior of dark energy US indicates a thawing quintessence field. Okay, it's a very long title. So.
Okay, good morning. It's my great pleasure to come back to Bengaluru, India again. And I'd like to thank Tarun, Subir, and Prabha, and all the organizers for inviting me here. I checked my record, and I found that I was in Bengaluru 10 years ago, almost 10 years ago. And at that time, I talked about the same thing. But at that time, I explained the method, and today I'm going to report the result. So there will be a big difference between 10 years ago and now. Okay, so this is one-page summary of my talk, and we measured the average value of dark energy crystal state parameter W, and then we measured the first time derivative of W as well. So about 3 years ago, we reported that the average W from G equals 0 to 0.7 is about minus 0.9. And we managed to have very small error bars. And it is 4.2 sigma away from -1. Therefore, we ruled out the flat lambda CDM model at 4.2 sigma level. And this year, we measured the first time derivative of W under CPL parameterization of W, and we measured WA to be basically consistent with 0, but slightly negative. And that means we do not find strongly evolving dark energy equational state, and also the most probable behavior of W of Z indicates there's no phantom divide crossing, at least before Z equals 0.7. So I'll describe more in details. So before I start to explain what we have done, I'd like to emphasize the need for small scale, the statistics on small scale to constrain cosmology to great accuracy. And the reason is we are running out of statistics from these galaxy clustering studies, because if you use BAO to constrain cosmology, the number of information you get will not be very much. So even if you obtain all the redshift of galaxies within the visible part of the universe, namely, suppose you observe all the galaxies out to the redshift 10, and then this moving distance out to redshift 10 is about 6,000 megaparsec, 6 gigaparsec, and therefore the number of independent elements within this visible part of the universe, galaxy world, is only about 10 to the 5. But if you use, for example, the Alko-Patinsky test, like the one I'm using, you can use information on 10 megaparsec scale, and basically the effective size of data is 1,000 times larger. So that makes a lot of difference. And of course, the statistics should be corrected for any potential nonlinear or non-Gaussian effect. And as we go to 10 megaparsec scale, you have to worry about the small scale nonlinear astrophysics. So you have to be very careful in choosing the kind of statistics. And the statistics we are using is the large-scale structure topology, which is very insensitive to gravitational evolution and biasing, and also the Redshift-Space two-point correlation function, which I'm going to explain today. And both statistics can be used at 10 megaparsec scale, which makes your data effectively very large. Okay, so let me explain how it works. So suppose we are living in a flat lambda CDM universe with omega lambda 0.74 and omega lambda 0.26 and W equals -1, of course. And you are observing the galaxies at the four corners of this blue square, and you are sitting here. And there are four scales, and all you get is a redshift of these galaxies sitting at the corner, and you adapt the cosmology to convert this redshift to co-moving distance. And suppose you chose the wrong cosmology, namely in this case, you overestimate omega matter and calculate the co-moving distance, and then you underestimate the distance, so this scale will appear closer to you, but also it's a bit squashed. If you underestimate omega matter, then the expansion of the universe is overestimated, and your apparent distance to this galaxy will be overestimated. So this scale will be showing up at larger distance, but also it's going to be stretched. So depending on the cosmology you choose, the shape of this object will be distorted. And this stretch factor is like this, as a function of redshift. In this case, you underestimate it like this, And in this case, you overestimate this. And therefore, if you use some object for which you know the shape, you can constrain the cosmological parameters that govern the expansion history of the universe. So this is basically how we are able to constrain the dark energy equation state parameter. Okay, so I'm repeating the same thing, but in different way. Suppose you have galaxy data, so you have angular position and redshift. You adopt a cosmology, namely out of Z relation, to convert redshift to moving distance, and now you have three-dimensional position of each galaxy. And therefore, you can make a map like this, and then you divide your sample into few non-overlapping redshift shells, and then calculate the correlation function in the two-dimensional space along and across the line of sight, and then you compare the shape in one redshift bin to another, okay? And then you have to take care of the expected evolution of this shape, okay? Which can be derived from a set of cosmological simulations and which takes into account the gravitational evolution and galaxy bias. And then you check if the shape of correlation function evolves given the cosmology you adopted. So you try many different cosmological models and choose the model which minimize the evolution. And that's your best fit cosmology.
Do peculiar velocities fit in there? Finger of God, etc.?
So the correlation function we use is the correlation function in redshift space. Okay, so we don't need to correct for the peculiar velocity. So there is slight difference compared to original Akopachizki test. In original Akopachizki test, one needs to know the shape. And in each redshift, you compare this known shape with the shape you measured. But in our case, we don't need to know the shape. We just compare the shape in one redshift bin to the shape in other redshift bin. So you only care for this difference. So you don't need to know the size or shape, and only the shape conservation is needed in this case. This makes our method independent of many other cosmological parameters, other than those that affect the expansion history. Okay, so the standard shape we choose is normalized redshift space two-point correlation function in this study. And let me try to explain why this is good. So here, this is a two-point correlation function calculated from embodied simulation at redshift 0, 0.15, and 0.5, okay? And this is the difference between these two correlation functions and this correlation function, okay? And you can see in this redshift space distorted correlation function, the amount of distortion in one point in this to another is of order of 1. Okay? So there's a lot of distortion, but the difference, the expected evolution of this shape is of order of 0.01. Okay? So it's 100 times smaller, and that is what you need to correct using simulations. So the correction can be made very accurately, and the uncertainty in the correction is another order of magnitude smaller. We use Sloan redshift survey data, which is broken into 6 redshift bins. The bright galaxy, so I'm using DESI data on that right now, so I'm a bit confused in names. This is the main galaxy sample, and the LOSI and CMAS. Okay? So we have 6 redshift bins. We decided not to use this EBOS, which has too noisy. The correlation function we measured in each redshift bin looks like this. This is the two-dimensional correlation function measured from the first redshift bin, which is the main galaxy sample. And this is from LOSI, and there are 3 data from CMAS. And if we overplot all of them, they look like this. So in this calculation, we adopted this lambda CDM. Okay? And you can see the shape of college functions all overlapping with each other. So by eye, you cannot see any difference, which means lambda CDM is already very good. Okay? So, but it turned out that it can be still improved, and there's other model which is better than this, better than lambda CDM. So this is the result from comparing the shape of collage function in 6 different redshift bins. And the 2, so this is the average dark energy equation of state parameter, W, and this is the omega matter, total matter density. And these 2 are the ones that affect the expansion history in this cosmologies. And in omega matter and W space, I'm also plotting other constraints. And our concern is this pink one, and BAO is up there. This is SDSS BAO, and this is supernova, and this is Planck CMB. And if you see only this low redshift probes, then there is one spot that overlaps with each other. So there is 1 sigma regions are all overlapping at one spot, but there is no good overlapping with CMB. So if we combine only these low redshift probes, without combining CMB, we get this constraint. And we found that W equal minus 0.9, and it's 4.2 sigma away from -1. And therefore, at this 4.2 sigma level, we can rule out lambda CDM. Sorry, it's not 5 sigma, but it's close to 5 sigma. Okay, so this was more than 2.5 years ago. Okay?
This is combining the 2, right?
It's a combination with BAO, basically. So, right, so yeah, this orange one. Okay. So the supernova didn't help much because it's basically parallel to our constraint. But BAO basically shrank our error bar a little bit. Okay, so they helped because it has some angle to us.
Why do you not include CMB?
I'll tell you later. Okay, that's critical point of my whole talk. Okay.
Can you say why CMB is so weird?
I'm not in that position to answer. Okay, it's CMB people to answer.
This is Planck 18.
18, yeah, Planck 18, yes. I think nothing has changed. Yeah. So in only 2023, still there was more than 1 year before DESI first year paper, and nobody was talking about deviation from lambda at the time, so it was not very well accepted at the time. But I show you it was confirmed by DESI itself 2 years later. So this is the DESI paper submitted this year, and you can see this is not DESI only. This is CMB plus DESI plus supernova, in this case uniously. Okay? And there's only one significant, one data point that is significantly away from -1, and that's the first bin. Okay? So these are not independent measurement. It's just the bin W measurement in different binning scheme, and others are not very well measured. But this one is clearly suggesting that W is away from -1, actually greater than -1, and the value is actually almost exactly the same as what we measured before. Okay? So we basically DESI confirmed our measurement. Okay, so this year we extended our analysis to measure the time derivative, average time derivative of W. So we constrain, now we have two more parameters. So including omega matter, we have 3 pre-parameters to constrain. So therefore, the constraining power drops a little bit. But still, our AP test is so powerful that we can still talk about very interesting constraint on W without combining with CMB. And WA measured here is basically minus 0.17 plus minus 0.304, and therefore is basically consistent with 0. Okay? And this is a supernova. And it's a bit difficult to see, but behind this contour, there's a blue contour. And this blue contour is the joint PDF of supernova and BAO, dash BAO. Okay? And if we combine this blue contour with this magenta contour, which is from AP test, we get this orange contour. So this orange contour is the joint constraint from SDSS AP and DESI BAO and supernova, Pantheon plus. Okay, so this is this, and it compares with the report in the DESI paper, DESI 3-year paper. This is from Planck CMB and DESI BAO and supernova 1A, and there are three different kinds of supernovae here. And if you look at blue or green here, and they can be able to say, basically this area is 3 sigma away, more than 3 sigma away from WA equals 0. So the main conclusion of this report is that there is evolution in W, strong evolution in W. But in our case, it's basically statistically consistent with 0, but the most probable W seems to be maybe much slowly evolving. So you may ask, what's the difference between this and this? And main difference is the inclusion of CMB data. Okay, and let me show how this happened. Oh, well, in another way, so this is the result I just showed you. And if I plot this as, well, in terms of W of Z as a function of Z, and this is basically what we predict. So this is the most probable Redshift evolution of W, whereas this green band is the most probable evolution of W reported by DESI paper, and there is fundamental difference. Okay, so here you see there is a phantom divide crossing at Redshift 0.4, whereas we do not predict, we do not measure any phantom divide crossing out to G equal 0.7. Okay, and therefore this suggests that the dark energy may be thawing quintessence, whereas here you have to think of some other models. Okay. But what is important is if you don't include AP test and also don't include CMB and only combine DESI and supernova, this is again consistent with our result without combining our result. So this is still, WA is still very small, and it suggests no crossing. So it's only when CMB is added, you get this phantom divide crossing at G equal 4. So you may wonder what's going on, and here is an explanation. So this is the constraint on W0 and WA from DESI BAO only. Okay? And they put this prior to WA to be greater than -3. If they don't apply -3, on the lower limit of -3, I don't know how far it will go. Okay, and the 1 sigma error bar and 2 sigma error bar may change as well. But anyway, accepting this prior, you can combine BAO data with supernova, or another supernova, to get this. And you can see this combination tells you WA, maybe most probable WA is slightly negative, but you cannot tell between WA equals 0 and this most probable one. So basically, these are consistent with WA equals 0. Now, let's see what happens if we add CMB. Okay. So this is the constraint from CMB only. So it has very weak constraint on these W parameters. And it's almost parallel to this. So if you combine this one and BAO, and the joint PDF is appearing over here. And you get very tight, very narrow contour. And it appears to be statistically very significant, but that is because they are not overlapping much. So if they disagree more, you may get even tighter constraint. And if you add this one with any of this, then you get this, because these two are basically cutting this contour vertically. Okay? So this is what you saw before. Even our data. Okay, so I overplotted this one to this. So so this is the joint constraint from this and this, and phantom crossing is due to the shift and slope of CMB. What I mean is, CMB is shifted to the left, and it's at the bottom. So whenever you combine some constraint with CMB constraint, and your value of WA is going to be more negative. So that's what's happening. So even our constraint, is this one, this pink one. So this is the one I showed. This is my main result. But if I also combine my result with CMB, the joint constraint will be this. So WA will move from -0.15 to -0.62, and I'm going to get phantom crossing. So you can see how big CMB constraint is, but how big the impact of CMB combining with CMB. Okay? So because your physics completely changes by combining CMB data, you got to be very careful. You cannot just rely on statistics. You should check the physics you're finding. Okay, so let me conclude. So I'm just repeating the same thing. So 2.5 years ago, we published our result on average W to be 0.9, and this, it is this point. This red point is the one we got 3 years ago. Okay, and this curve is what we got this year, and we see there's no phantom divide crossing up to 0.7, and the kind of Dark Energy you can easily think of is this thawing quintessence field. So this is my conclusion. Thank you.
So we are 10 minutes ahead of time, so we have plenty of time for questions, and if there's more time, we can go back to the previous speaker also. Okay, so let me ask Dimitri.
Do you need to press something?
Just, yeah, I know. Yeah,
okay. Chimang, can we go back to your result, which were between 23 and current ones, where you don't have a running yet, but we're already combining some experiments?
Tell me where to stop.
Yeah, go. Yep.
This one?
This one, yeah. So here you already include Planck, and your W0 did not shift.
Sorry, I'm not showing my result. This is DESI.
Hmm?
Back one more. Here? Here?
No, that was...
This is my result.
The next one.
My result. And this.
So this includes Planck, right, CMB?
Yes, the CMB, DESI BAO, and supernovae, or 3. No AP test.
Oh, yeah, no, when it is confirmed, right, so...
this is confirmation of our
exactly,
result.
it wasn't yours, but so the question is that here you highlighted that your W0, which is obtained, is exactly like you did in 23, right, 0.903.
Right.
Right, but it did include a Planck. So
This
why
one-
did it not shift to lower values, to more negative values, right?
Well,
I was a bit surprised that this combination gives the same omega effective as you had in 23. So. Hmm? Oh, it's Redshift bin.
Yeah,
but
yeah.
The other reason they might be using the reanalysis of Planck. So there's a difference between Planck 18.
That could be the.
Doesn't change much.
No, it changes quite a lot.
I mean, in this plot doesn't change much.
In this
PR3.
Okay.
Alone,
I think this point is quite stable in their analysis.
Yeah, because your final result highlights the fact that Raman is changing significantly when you include the Planck, but also omega 0 changes a bit. And,
Right.
and here there was a moment when omega 0 didn't change while Planck was included, and that kind of drew my attention. So how this minus 1.5 did not affect
Right, so I think
omega
the
effective
main
much.
difference is in this, the slope is larger compared to ours.
Yeah.
Okay?
Slope for sure.
So average value over here is about the same. So that's what's.
Dick, yeah.
Yeah, so I want to concentrate on that set of points as well, because this was a comment made yesterday, I think by you, which is that the main result is that there's a discontinuity, more or less, in omega m results, and that's driving everything, and that's the reason that the W is where it is with the DESI plus supernova data. And so one of the things which I don't really see with these analyses is where the most significant information is coming from as a function of redshift. So for example, if you were to plot the weight, effectively, or filter, if you like, of the AP method in terms of the data, what would that look like as a function of redshift? Is it more focused on low redshifts or higher redshifts?
I didn't specifically focus on that question, but you expect this kind of shape evolution depending on cosmological parameters you adopt. So if you fix W to -1, and this is the amount of difference in the shape evolution, if you change W, this is rather extreme difference. The omega matter is fixed, but W
but that's
is
with
varied.
this one parameter variation, which is not really such a good indicator.
Right, but there's more information coming from low redshift data.
Exactly, which is where this discontinuity in omega m is apparently appearing, right? Because the omega m from Planck is higher than the omega m that seems to be coming out.
Yes.
A bit lower, yeah.
A bit lower, sorry.
Planck is lower than?
No. Is it?
Planck is something like 0.32?
No, Planck is higher, so.
Yeah, Planck is higher, yeah. So it goes higher to lower. And And that's what the large-scale structure data is pointing to, and then everything else is following from that. And it's making assumptions, of course, that omega m goes like a to the minus 3, which maybe it doesn't. So there are all sorts of issues that arise in the context of this. But the thing that is, I think, really fundamental here is whether or not one's really got a dark energy evolution effect, or one has a puzzle which may have discontinuities in it, or somewhat discontinuities in it. It may not be sharp, but what appears to be the case is there's a region around us with the lower density than what you get by extrapolating from Planck with the a to the minus 3 law. And then the issue is, can one unravel that to say, this is what happens? And you know, you showed it in that nice W plot, but there was another plot that was in the DESI results in which everything was kind of being focused at a low redshift bin as what the deviations were. And so that's the sort of thing. It's the same thing that we do when we look at templates with the microwave background, which is what you were doing, right? You were basically making a template associated with derivative with respect to W. Yeah. So that's got a coherence associated with it, but that isn't necessarily where the data is. I mean, you have a template, and the template's going to grab onto something in the data, which you might call a residual, and it doesn't mean that it has anything to do with the template curve. It's just that it's grabbing a piece of information from it, and so there should be some kind of better figure of merit. Planck ran into the same problem with A lens and all of that. Everybody said, A lens, A lens. It didn't look anything like, the residuals did, or the mode functions didn't really look anything like A lens. It's just that they only stuck in that parameter. And that's the central issue with the residuals that come when you're dealing with a deviation from, let's say, the tilt-a-lens CDM. I'm looking for your comments on this. I obviously talked for too long.
Short reply, and then I think Arman has replied.
And I won't say anything more.
It's a difficult question to answer, but I just want to say omega, I mean, this W is equally doing important role in this doing equally important role in this constraint because they are all correlated. So this contour is actually the three-dimensional ball in this three-dimensional parameter space, and they are correlated like this. Okay? So, yeah, if you change omega, then W changes as well, and so on.
But basically, probably measuring something like growing mode G of Z.
Growing
mode G of Z.
Growing mode?
So maybe let Arman.
Yeah. Okay. Yeah.
You're not supposed to ask questions.
Yeah. I mean.
You listened to my talk many times already.
Yes, but that's why I have to give I mean, an unfortunate situation to make the same comment. I mean, about your results. I mean, to me, I mean, it's too good to believe. Very small contours, which is tinier than everything else, just with the supernova BAO. I'm not going to talk about that. But there are some misrepresentation of some of the things. For example, DESI didn't confirm your results. I mean, W constant minus 0.9 is ruled out by DESI at more than 5 sigma. And all these expansion histories are correlated. So we cannot just get a part of it at the low redshift and says that, this is, the first beam is consistent and the rest is not. So it's not the same thing. There's not the same confirmation. And some of the things about the BAO and the CMB, they're overlapping at the 1 to 2 sigma, right? So statistically, we are allowed to combine them. And there is nothing wrong with that. I mean, there are basically like a 20% chance that a true model, the underlying true model, might basically have a representation in that part of the parameter space. And the priors on the WA, lower than -3, doesn't matter much because dark energy density doesn't really change much for the large negative WA. So in some sense, I think if this analysis is correct, it should explain that why is this different from the DESI. I mean, I'm not saying that which one is right, which one is not correct, but I see inconsistencies here rather than a consistency, and no confirmation. Yeah.
Okay, I'll answer that question.
Just quickly, because Subodh has one more question. Yeah.
So I didn't find anything wrong with DESI BAO. Okay? As I said, if the DESI BAO and supernova combined, also consistent with our result, indicating no phantom divide cross. But it happens only when CMB data is combined. So I think the Raman is making comment just to make a counter argument. So that
so maybe you can discuss this later. We can and discuss. Yeah, last questions by Subodh.
Yeah. So so these banana plots that we're seeing here, you're scanning over two parameters, and
three parameters.
Three parameters, right? So, if, for example, I have maybe sort of like a structural constraint saying that I don't want, I can't imagine W being less than 1, everything would be very different, right? For example, if I'm fitting people's heights, I would never take seriously a banana plot that went over negative heights. Right? Or if I was doing the same thing in genomics and I saw something with negative admixture, I wouldn't take a banana plot series with negative admixture. Going less than -1 is for omega is very problematic from a fundamental point of view. Right? It's unphysical, right? There's no stable background that does it, and so I get that. I get this is what it's doing. It's just this is curve fit. I'm not criticizing you or in general. This is a community-wide question. So maybe I'm going to ask a question. Do you have any idea how this would look like if you said, I actually have a strong theoretical prior that omega can't get less than 1? It'd be very different, right?
I don't know what your question is.
If you don't allow, if you just know, in the same way that I would never fit, if I saw a banana plot for, let's say I have a bunch of people's heights and I know some information, I know some correlations, and I have some prior distribution, and I saw the banana plot going over someone's height being negative, I'd be like, well, that's crazy, right? So negative height is meaningless. Why am I doing that, right? So I happen to think that negative omega is as meaningless as negative height, right? And so my question is, how would your conclusions change if you just restricted your analysis to throw away anything less than -1? It's not prior driven.
Sorry.
But it would do something very different to these plots, right? It would.
You'll get a bad fit to the data. Your data won't. The model won't fit the data.
That your two-parameter model won't fit the data. Your parameterization of the model won't fit the data. Right.
So the fact that it's ending up somewhere where W is
Yeah.
-1,
Yeah.
in the absence of the priors that you're saying you put in, indicates that you might be getting something.
Would you say negative height is a prior?
No. For example,
Right.
so for example, if you have dark matter, dark energy interactions, W going less than -1 is only an effective parameter going less than -1. You don't violate that energy condition.
Well, dark energy already violates the strong energy.
The null energy. I'm just interested in the null energy condition, right? So, but it's really just okay. Let me phrase it as a statistical, like a fitting, an inference question, right? Let's say I have some strong structural constraints on where the parameters can range, and it's a discrete cutoff, right? And then if I allow it to sort of float off, everything would look very different in one case versus the other, right? Yeah.
Exactly. There are many models in which,
Theory, sure. What you're saying
if I cast it in this form of energy density is evolving with redshift, and then you assign an equation of state with that number, it may turn out to be something with a, unphysical kind of equation.
Sure.
But that's like because you're massaging your equations into a particular form.
Right. So you work within a parameterization, i.e. a model parameterization, right, with a certain number of parameters. It could be something else, you don't know, but within this you're getting something. Is that the statement? Yes. Okay.
So you don't know physically what it is. You're not trying to.
So anyway, so I think, yeah, go ahead. Quick comment.
The takeaway is that there is something interesting that I don't know whether one should take the specific value of W0 and WA very seriously. But the fact that it's not W equals -1 being consistent is what everybody is emphasizing.
There's a tension between BAO and the if you do it like this and you get if you parameter like this to resolve the tension, you get this. If you force it to be over -1, you won't resolve the tension. Doesn't mean that you're not right.
So I just want to make, okay.
Thank you for answering for me. There is a degeneracy direction over here. So if point is above this line, then it will stay above -1. But I didn't put any prior knowledge. I just probed all the possible combination of these two, and yet I got this behavior. So that's all I can say.
Okay. Any more questions, discussions? So Glenn, your question is answered about the CMB. Okay. Yeah, Alex.
If you know the correlation function, the next one. Yeah, that, for example. So if you went to, like this, if you went to very, very high distances in this correlation function, you could start testing the homogeneity and isotropy assumption that we're making about the universe, right? And we then connect to what was discussed yesterday. Now, I don't know if you have enough signal to do it, but this is effectively what you, because here you're assuming homogeneity and isotropy, and you're deriving parameters, but you could.
You mean the along radial direction?
Both, right? So what you're testing here is whether your correlation function,
observed field.
What you're testing is whether your correlation function is consistent with the homogeneity and isotropy, and you modify your background until that's the case. So what they discussed yesterday is there's evidence for deviation from isotropy at redshift a few, or the bulk flow is even lower. So if you could, this is only at 20 megaparsec, but if you go to, what was it, 200 megaparsec or something, you should be able to test what they are finding. Now, I don't know if you have enough signal there, but that could be interesting to think about.
As you can see, we use the shape of correlation function below about 20 megaparsec, about 30 megaparsec.
Right.
From 6 megaparsec to 30 megaparsec is the range we use.
Right.
So we don't go very large separation.
Yeah.
Because the statistics, there is a shot noise is important, and also the cosmic variance is also important there too.
Of course.
But both are very small on small separations. And I don't know how this assumption.
It'll be interesting to see how far, how high, to what distance you can go with this measurement, and see whether you can test the assumption.
Could you go to even 300 megaparsecs? Could you increase the scale? What he's asking is, instead of adjusting the background to suit fit, could you use this as a test of the underlying assumption, is the question.
Yeah, well you can compare the shape of correlation function at much larger scale.
Right.
There is a
where the short noise would be quite high, you're right, but with the forthcoming data.
On those scales, we also have to worry about this plane parallel approximation of correlation function and so on. So that's another complication.
Yeah.
So, but that can be basically dealt with by using mock samples. So, okay.
Okay, any other questions for this thing? Okay, before we break, any questions on Alex's talk? I think I had to cut down some of the questions.
He didn't finish answering the thing about the elephant in the room.
No, just very quick, yeah, just very quick.
Did you want to say something? Could you finish your answer that you couldn't finish? About the thing which is going beyond the subject of this conference. No, your talk. The unexplained overall shear. The embarrassment. Let's hear about the dirty dinner.
Let me explain. So what I showed is the map I showed, which is the map of the projected matter density, sometimes called convergence, over the sky, right? And this is done by measuring the shape of galaxies that give us an estimator for the shear that we turn into a scalar, which is projected. And what I was showing you is has to do with the variation of this shear over the entire map, right? What Subir is asking is what happens if you take the mean shear over the entire survey area And he's noticed in the weak lensing papers that if you do this, you get a significant mean shear. Okay? So in other words, it means that the galaxies over the entire survey area, which is a huge volume, their shape doesn't average to circular shape. They have an alignment coherent on very, very large scales. So that's what and of course I know what you think is, could this be an evidence for anisotropy or homogeneity? So that's a very interesting question. So it is true that in many analyses we get this, and the thing is that if you average over all the galaxies in the survey, as opposed to looking just at pairs to do correlation functions or a map in pixels, you get a very, very, very small error. So your sensitivity on the mean shear is extremely high, and it's even higher than the requirement you need to measure the two-point function or make a map. So the calibration of the instrumental effect, like the point spread function and the image noise properties and all that, are not done to that level. And so we say, okay, there must be some residual systematics, and we ignore the mean, and then we do the two-point function. The mean is so small that you don't even need to subtract it. But nevertheless, it's there, okay? And it's true that we could look at that and try to test the homogeneity and isotropic condition for that. In order to do this, as I was telling you, and that's something I wanted to ask yesterday, it would help us if you can give us, I know people don't like models, but if you can give us a model of the large-scale bulk flow, large-scale anisotropy, that would be useful, so that it gives us a bit of a guide at what we're looking for. Because what we could try and look for is not only the mean, but also some kind of a dipole or redshift dependence or something to give us a guide. Because we're going to have to look for a very weak signal in a regime where we have systematics. Right, where the requirement for the analysis was not done to do this. So it would be very useful if we can have a model or a set of simulation with these bulk flows, which is physical, so that we can have a bit of theoretical guidance. That's what we're looking for. Because I think just looking at the mean shear, I think will be quite hard. Yeah. Yeah. Thank you.
So is this mean shear observed in just one survey or all?
In many surveys. Yeah. In many surveys, we get a significant non-zero shear. Yes, different survey, different systematic, but they're different. It's not the main. Yeah, so to be clear, it's not the same mean shear. Huh? It's different. So,
Alex, I had a question earlier. I mean, this is related now. I mean, my question was, there was a period where weak lensing was supposed to be a very, clean measure long back, and then we realized that PSFs and all are very ugly. Where do we stand? I mean, now I understand that is still the limiting point.
So I think there was the first detection in 2000, and there was a period where weak lensing was growing, and we were more limited by the image, the size of the image, and the quality of the cameras and so on, the linearity of the cameras. And then it's true that we got into a difficult time because we're limited by systematic and analysis. And it's only with the advent of stage 3 surveys, KIDS, DES, and HSC, that we could overcome this systematic, because we had so much more data with more recent telescopes that we had more signal to work on the systematic. So now it's back on a good footing, but you see it's hard analysis. I mean, one thing I want to say, like all of these measurements are systematics limited. I would argue the CMB also, and the supernovae and so on. So it's also systematic limited. The analysis, I could give you an entire lecture on the analysis steps and the systematic. There are many. We're limited by this. It's mainly intrinsic alignment, the redshift calibration, actually, and some shape measurement systematics. But now we've made, I think we're systematics limited, but we can quantify these errors quite well. So that's where we are.
Question. So this global signal that Subir is referring to is in the E?
It's a constant. It's a constant shear. So it's a DC. It's a DC. It's the mean shear. So all the galaxies are slightly oriented in one direction.
Only measuring the E, right? As far as I could make out the P.
No. If you look at the shear, you're not yet doing an EB decomposition. Okay. You only get EB decomposition if you have a map and you can So it's a bit having like a mean polarization in the sky. It would be similar to this. And he would ask you, so it depends on the survey, but we have, I don't know the latest, but it's several sigmas. I mean, it's 5 sigmas. So it's significant. It's significant. But as I said, it's very, very small. The significance is clear. I can't remember but it's significant.
But
it's significant. Yeah.
You said different surveys give you different directions.
Mm-hmm. Yes.
But if you take a large survey and you split in two, in the same survey you have the same direction,
I don't know if people
you have large scales.
Yeah.
And could it be this rather than an overall
don't know
anisotropy like large-scale tidal fields?
Yeah. That'd be interesting. I don't know if people have done that. Again, because it's so small that people don't worry about it. But as I said, if we had some kind of guidance for the amplitude that we expect, so we can take the measurement and anisotropies that are found with bulk flows or the radio galaxies and infrared, and if we could translate that into an amplitude that we expect and perhaps a large-scale, model for how it should vary in the sky, maybe we could look for it. I don't know if people have done this.
So I see the next speaker is already getting jumpy. We're already 15 minutes into the break. So let's break now, and I think we'll come back, I think 11:26, it's now 11:06. Okay, so let's keep it 20 minutes.
It's very interesting. As he said yesterday,